All right. All right. So the first speaker in this afternoon session is Professor Rama Govindarajan from Bangalore, and she'll be talking about multiphase dynamics near a single vortex and its relevance to turbulence.
Thank you. Let me first say how happy I am to be here. So thanks a lot to the organizers. Today, I'll be talking about two situations where we'll try to solve the problem exactly using a single vortex, and then we'll ask what its relevance is to turbulence. The first one is two immiscible fluids, so which are on either side of this interface. And this interface rolls up in this manner. And the next problem is about particles in a fluid. And the fun part about these two things is we're going to encounter these two spirals as part of the large distance dynamics. And one of them is the opposite of the other. If you see, like this one is r squared theta is a constant, and the other one is theta over r square is a constant. So the limbs go further and further apart as you go away. And in the other case, they go the other way around. So these are two exact solutions that we're going to encounter at large R. Incidentally, both of these are generalized Archimedean spirals. Doesn't work. I'll use this for a minute and then. Okay, so let's start with what the relevance is of a single vortex that we're going to study to turbulence. So like here's a picture of 2D turbulence. You see that if I start a simulation with random noise in the, vorticity in the form of random noise, as you see in the square up there, that will, organize itself into these very concentrated patches of vorticity in 2D turbulence at least, and similar things in 3D turbulence. And this is well known to last for a very long time. Like these patches try their best to axisymmetrize and then they live for a very long time. And their profile of vorticity is a Gaussian. So they're called Lambosine vortices. So Lambosine vortices are a very, very standard thing in turbulence. So now we're going to talk in the first problem about what if you have turbulence and then you put two fluids there. So you have these interfaces. So we're going to treat this as the building block where there is one vortex, a Lambosine vortex, and a flat interface with density 1 and 2 on either side of it, and a surface tension for this interface, which is sigma. And this thing can be worked out analytically, but you can work it out for all other kinds of geometries as well, like whatever kind of interface and whatever kind of vortex you have. So, so this part of the work was done primarily by Rashmi Ramadugu, who actually is a joint student of Prasad Perlekar and me, and she submitted her PhD thesis about 2 or 3 days ago. And I'll be referring to some old work which was done with Harish Dikshit. So the moral of this thing is the following. You have any vortex and any interface between two fluids. And if that's the case, you always have a variety of instabilities, and we're going to talk about that. So incidentally, we are all, normally used to thinking of surface tension as a stabilizer, right? But here we're going to see it as a destabilizer. And then we're going to also talk about buoyancy-driven instabilities because there's a density difference on either side. And all of these, both these kinds of instabilities create small scales in the turbulence. And that's what we're going to talk about. Oh, it's not working for changing. Okay, thanks. Okay, so first we'll address two dogmas and we'll talk about what happens in the neighborhood of a vortex. So the first is like here is the Navier-Stokes incompressible for, when there's two densities in the flow, there's a rho naught plus delta rho on one side and rho naught on the other side. So normally under the Boussinesq approximation, when you come across an equation like this, and you say the Atwood number, namely the density difference divided by the total density, if you say that this number is much less than 1, so you will neglect this part of the density variation and you'll retain it only here. So you can actually show very easily that that will be wrong if you have a vortex whose circulation gamma is such that there is this Froude number you can construct. So if the vortex is spinning around very fast compared to gravity, then you cannot make the Boussinesq approximation. So this is a thing you can work out for yourself. So that is one dogma about making the Boussinesq approximation at small Atwood number. That can only be done if the vortex is not too powerful. That's point one. The second dogma is that surface tension stabilizes. So we all know surface tension stabilizes, but we also know about the Rayleigh plateau instability, which is, you know, very, very old. And the interesting thing here is, so suppose you have a cylindrical, you know, column of fluid. It is subject to instability like this, and then it will break into droplets. So the interesting thing is, because it's three-dimensional, this surface perturbation, undulation, actually has less surface area than an undisturbed cylinder. So surface tension wants to reduce surface area, and because of that, the Rayleigh plateau instability happens. There's another recent, very nice instability, which is coming out of surface tension added to the Taylor-Coldfield configuration, which I won't talk about, but it's a very beautiful paper. We're going to talk about how vorticity is generated on the interface due to this, and several instabilities occur. Okay, so we're going to talk about two mechanisms for vorticity creation, and both of them are on the interface. So here's the vortex and here's the radial coordinate r. This is a Lambosine vortex and this is any radius r. So the interface is arbitrarily shaped like this. So there is a density jump across the interface and there is a surface tension force acting normal to the interface. So like, yes? Okay, so we can take the curl of the Navier-Stokes. We're going to now neglect gravity from now onwards. We're going to take the curl of the Navier-Stokes to write the vorticity equation. And you see that vorticity can be created by these mechanisms. So we're going to not worry too much about viscosity. This whole mechanism is inviscid. That's why out of the three non-dimensional numbers, I put Reynolds number very small, because I mean, so long as it's high enough, it's unimportant to our problem. So there's the Weber number, which is a ratio of, and this UC and RC are typical sizes of this vortex, size and velocity of this vortex. And then this is the Weber number, where sigma is the surface tension. So higher Weber number means lower surface tension. And the Atwood number we saw before. So this term goes to 0, but these two terms actually create vorticity on the interface in the form of a delta function, because this quantity, the baroclinic talk we saw in Greg Cheney's lecture a couple of days ago. So this is grad rho cross grad p. And so like if the density gradient and the pressure gradient are not collinear, you'll get this baroclinic torque. And the other one, I'm calling it capillary torque for want of a better word, but if somebody has an objection to that, like, please let me know what's a good term. So incidentally, you're going to get vorticity creation everywhere on the interface due to surface tension, F sigma. So now let's see how that works. Yeah, so here's a Lambosine vortex and it's an exact solution of the Navier-Stokes, and the vorticity looks like this. The velocity looks like this, and this is the velocity scale that we are using. So what happens is, if you start with the Lambosine and in the limit of very small RC, you get a point vortex. So so what happens if you start with a flat interface and a Lambosine vortex here? You can show that you can actually compute the exact shape of the interface as a function of time. And you will see that at large distances, it's going to be a Litwus spiral, which you can actually work out by hand. And this spiral is ever tightening as time goes on. So instead of being r square theta as a constant, it's a function of time. So that's this ever tightening little spiral. So the thing here is that you have these density interfaces at every arm of the spiral. Whenever you're going from light to heavy, heavy to light, you'll get an instability. It's exactly like, when there's gravity down and you have a heavy fluid up and a light fluid here. Suppose your interface is like this, it's going to create baroclinic torque and go like this. So you're going to get an instability just because heavy is over light. Here you'll get an instability because heavy is inside light. So at every alternate arm, you're going to get instability, which is basically the centrifugal Rayleigh Taylor instability. So now the interesting thing is that there is baroclinic torque created and this capillary torque created. The reason for that is that a spiral is not a circle. If a spiral was exactly a circle, then there'll be no variation in curvature, and because there's no variation in curvature, there'll be no capillary torque, and this term also will not exist. But because of this small teeny angle between a circle, and the circle is shown by the dashed line, you will see that there is baroclinic torque, which you can actually write down by hand. It goes down with the distance from the center and also goes down with time. So you can write down the torque creation. You can integrate this in time to get what is the vorticity at the interface. So that's what's going to happen with the density gradient. What happens with surface tension? So this, we return to our dogma. So the dogma says that surface tension hates, very curvy or, surfaces with lots of surface area. It tries its best to flatten everything out and reduce the surface area. And we're talking in 2D here. So like the dogma is surface tension stabilizes high wave numbers and does very little to, long wavelengths. Like if there's a very weak curvature, then surface tension doesn't do too much to that, but it tries to stabilize these things. However, we're going to see that there is a Kelvin-Helmholtz instability created by surface tension, and that's because of this capillary torque term, which is creating a vorticity everywhere on the interface. So whenever you have a delta function of vorticity, you have a velocity jump across it. That's given by that, and the velocity jump is immediately subject to Kelvin-Helmholtz instability. Now, if you had, and here viscosity is important, suppose you had like this interface which was inviscid, then by Kelvin circulation theorem, you can only have vorticity wherever there is an interface. You cannot generate vorticity anywhere else. So this interface will keep getting distorted, nonlinear, and into very weird shapes. And although surface tension hates it, it's going to do nothing about it. It's going to go on creating vorticity here and so on. However, because we are in high Reynolds number and not in inviscid, perfect inviscid flow, surface tension can actually stretch out the interface and make it flat. It will go on trying to do this. And these vortices which are on the interface can actually peel off on either side. So you can get vorticity peeling off from the interface due to viscosity. Okay, so this is a simulation, but it might as well be theory. This is the initial interface we start out with. Fluid 1 on one side, fluid 2 on the other side, flat interface with a Lambosine vortex there. And after time t, this is what happens. The shape here is different from the shape outside, and we will treat them differently. So Q is basically the radius divided by RC, the whole square. So it's a square of the non-dimensional radius, and C is just a constant. So after lots and lots of algebra, you can actually get some lowest order solution for very small distances from the center, and you'll see that there is a velocity jump created, the Kelvin-Helmholtz instability giving one, which goes quadratically in time, and it's divided by the Weber number. So if the surface tension is 0, there is no velocity jump created. And for very, very large distances away, the lithospiral, everything about it. And here the density difference also can give you this centrifugal Rayleigh Taylor and spiral Kelvin-Helmholtz instability I told you about. So you get a velocity jump here, which is negative something created by surface tension and plus or minus something created by the Atwood number, namely the density jump. So the point is that this can act, I mean, either to aid this or decrease this. So the instability can be modulated by the density gradient. And, you know, like by standard methods, such as in Chandrasekhar's book, we can write down the growth rate of this instability, knowing that it's Kelvin-Helmholtz, and omega is the disturbance frequency, whose imaginary part, if it is positive, will give you a exponentially growing instability. And that is, this thing is under a square root sign and it's plus minus. So if this thing is negative, then you get a positive imaginary part of the disturbance frequency, and so the thing will become unstable. So here you see there are two terms. This is a stabilizing term and this is a destabilizing term. So on the face of it, surface tension stabilizes, especially if the wave number is very big. That means the perturbation is very rapid. Surface tension stabilizes. But remember that grad U, delta U is also created by surface tension. So like when you write that one down, and we know what it is well inside the core. So you see that there is Weber number on both sides. Surface tension stabilizes and surface tension destabilizes. So it's competing against itself, and at large time, this is the destabilization is going to win. So you can actually get a condition for this surface tension driven instability. Now this is, remember, extremely general, like anytime you have 2D turbulence and even 3D turbulence with two fluids which are immiscible, you're going to have this instability. You're going to have this surface tension driven instability. It's extremely general. Okay, so like now what we did is we did simulations with a single vortex. We solved the Navier-Stokes properly for a single vortex with first no density jump, just surface tension. And you see that the theory answer, we can, I told you, solve it exactly everywhere in the flow. The theoretical curves at time equal to 1 and 2 are given in the solid line, and the simulation results are given by the symbols. And you see that the simulation is doing quite well. So the, you know, thing that we wrote down theoretically is not bad, or the simulation is not bad, whichever one you want to test against the other. And so you have this vorticity being created on the interface. This is done by Basilisk open source code. So
could I ask a question?
Sure, sure.
So can you say what the colors are? I was thinking this is density, but then there's, it says same density on either side.
Sorry, this is vorticity.
Where's the vorticity? Okay.
Yeah, yeah. So the red is 0 and the black thing is one sign, small amount, and the blue is another sign.
Thank you.
So it's exactly what I've plotted there in color.
Thank you.
Sorry for not explaining that.
Yes.
So that's at time equal to 1. And at a later time, you see these vorticity patches, you know, peeling off from the interface and going off into the flow. So basically, the theoretical estimate of when, at what time this will win is pretty decent, even in the nonlinear case. So now let's watch a couple of movies. So the first one is at very high Weber number, namely very low surface tension, and this one is at high surface tension. So let's watch those two. So nothing much happens in the first one. And in the second one, you see this instability, you know, taking off. And you see that this surface tension has brought back the interface to pretty flat. But the rest of the flow is full of vorticity that's thrown away from this instability. And now that was inside the core mechanics that you saw. What happens outside the core is a much more complicated expression. It doesn't really matter. But here you have you know, an Atwood number driven centrifugal Rayleigh Taylor instability, which is coming from the fact that there is a radial gravity or a centrifugal acceleration away from the vortex. It's just coming out of that. It's a standard Rayleigh Taylor on alternate arms. There is the standard stabilization by surface tension. M is a circular wave number now. And there is the spiral Kelvin-Helmholtz instability, which is created by surface tension and density contrast. So surface tension always creates it. Density contrast sometimes aids and sometimes acts against it. And we have good agreement with simulations in both inside and outside limit. And in the intermediate regime, we need to do the full solution and all the mechanisms act together. Okay, so that was about the role of surface tension when there was no density contrast. Let's do the reverse, which we did long ago. We threw away the surface tension, but kept only the density contrast. And all the Rayleigh Taylor and spiral Kelvin-Helmholtz instabilities, they appear in this, and the stability analysis and this agree amazingly well. So this is what happens near a single vortex. And this is just a collage of things where, you know, there is density contrast plus surface tension and a variety of things happening. Now we did a proper 2D simulation with two-dimensional turbulence. This was our initial vorticity distribution, which we got from running Navier-Stokes without the interface. And then we just put in this flower-shaped interface, but you can put any interface and you'll get similar answers. So just to have a general interface, we put that one at the initial time. So the black is one fluid and the white is another fluid. So when you have weak surface tension and strong surface tension, in both cases, you see a lot of vorticity being generated. Remember, like if there was no surface tension, you would not get any vorticity in these white patches. Whereas you see, you know, a lot of vorticity being generated, and here when the surface tension is high, it's particularly bad. So you see a whole lot of small scales. So that's what you're seeing in the full two-dimensional decaying turbulence simulations. So the point is, and this is the spectrum, the EK versus K. You see that as you increase the surface tension, the small scales become more and more and more energetic. So the only difference is that now we know where it's coming from. We could have just done this simulation and seen the small scales, but now we know where it's coming from. And the Hinz scale, which is like basically telling you how big a given blob is going to be. So like if you look at this, you see that the interface, which started out like this, has peeled off into, you know, tiny bubbles of fluid 2 in fluid 1. And these bubbles have some characteristic size in this case and this case. So we can pull out that characteristic size and compare it to the Hinz scale. So Hinz, the argument is that when inertia, when the Weber number, local Weber number is order 1, the bubble will pinch off and become, you know, separated from the rest of the fluid. So, I mean, turbulence can make bubbles of size given by where the Weber number is 1. That's the Hinz argument. And you will see that this is our scale, which we estimated from our numerics. And this is the Hinz scale. And of course, there is a prefactor there, but it's pretty proportional. So this is the first part of my story, where we've seen that in multiphase turbulence, multiphase turbulence is very different from single phase turbulence. And the main reason is that you have these, you know, a huge amount of small scales coming in, and the small scales keep increasing as the surface tension increases. So this is very different. And the reason that this is happening is a variety of instabilities. There is a spiral Kelvin-Helmholtz, which is created by surface tension and by density contrast. There is a centrifugal Rayleigh Taylor, which is created by the density contrast. Okay, so the summary of this part is surface tension can destabilize a generic interface apart from stabilize it. So it destabilizes it by creating vorticity at the interface. So this happens all the time for any generic interface, so long as the curvature, the curl of the curvature is not 0. In other words, the curvature is not constant. So if it is a perfectly round or perfectly flat interface, then this will not happen. But any other generic interface, it will happen. Density difference can stabilize or destabilize even without gravity due to non-Boussinesq effects. That is to be remembered. And the mechanism is through interfacial vorticity. And the take-home message for a meeting on turbulence is that the turbulence spectrum is way more energetic at small scales due to this mechanism in multiphase flow. Okay, so let's go to the other part of the story, which is about small spherical particles near a vortex. So yesterday you listened to Jeremy Beck's talk on this. So you already have been seeing it in this meeting. So like what happens in turbulence when there's teeny particles. And what we're going to talk about is a situation where the flow has a very big Reynolds number, but based on the particle and its relative velocity compared to the local fluid, that Reynolds number is very, very small. So the particles are in Stokes flow. Particle Reynolds number is very small and the turbulence Reynolds number is very large. So this is the situation we are going to talk about. And this situation, just like the previous one, we found some instabilities which explain something. Here the motivation is somewhat different. The motivation is that, you know, when you have a big turbulence, like in a cloud, you want to simulate like many meters on one side, you want to simulate these big boxes. And guess what? There are about 1,000 teeny water droplets inside each centimeter cube. So obviously you cannot do a direct numerical simulation accounting for each particle's dynamics. So how do we do this better? That's the basic motivation. And so we are putting this same old Lambosine vortex because it's all over the place. And then we're putting particles at various radii from the vortex and we are studying their dynamics. So why are we studying their dynamics? What happens to particles in turbulence? You will see that, like Jeremy said yesterday, the vertical regions are getting voided due to centrifugal forces. And so, and the particles are collecting in non-vertical or strain regions. And the color, which you can't see, indicates that some of these particles are accelerating phenomenally relative to the fluid. So they don't passively follow the fluid. These are inertial particles which get centrifuged out of the vortex, and so they do this interesting dynamics. But let's focus on just one vortex and understand the dynamics very close to it. So first I want to introduce you, and this is work being done by Divya and Saumya. It's not yet published. So the thing I want to introduce you to first of all is this magic length scale, which we use for non-dimensionalizing everything. And the magic length scale is created out of gamma, which is the circulation of the vortex, and tau, which is the time response time of the particle. So there's a particle property and a vortex property. Both are connected to make this length scale. And once you use this length scale and the particle time scale, so the particle time scale tau is just a square, where a is the, you know, teeny radius of the teeny particle. So just to fix your thoughts, in a cloud, this teeny particles could be order of 10 microns, whereas the Kolmogorov scale is something like sub-millimeter. So the Kolmogorov scale is way, way, way bigger than the particle. So it's a square divided by 3 times kinematic viscosity times this capital R. And this is an important non-dimensional parameter for us. This is effectively a way of representing the density ratio between particle and fluid. So if you have an extremely heavy particle where rho p, the particle's density is way higher than the fluid density, then capital R will tend to 0. So remember that for an infinitely heavy particle, capital R is 0. And capital R is 1 when the two are neutrally, when the particles are neutrally buoyant with the fluid. So that is to be remembered. We are going to talk about heavy particles where R is between 0 and 1. So now, and we have this time scale of the fluid, which, you know, we saw earlier in the surface tension case as well for the Lambosine vortex, which is some typical vortex size divided by its circulation. So, and based on this fluid time scale and this particle time scale, we can write down a Stokes number. And the Stokes number just goes as 1 over b square, where b is just the thickness, typical thickness of the vortex in these length units. So this is now the unsteady Stokes equation for a particle, for a small spherical particle in this flow. So this is unsteady Stokes, where Q is the difference in velocity between particle and fluid. So you have this, in terms of this velocity difference, the Reynolds number is very small and based on this size A. So this is the complete unsteady Stokes equation for a spherical particle. It's called the Maxey-Rayleigh equation. And normally what people do is, I put this in a different color. I don't know whether you can see the change in color. Normally people truncate here and they never use this term. We're going to come to that. We're going to come to why it is in the very next slide. And so this is what people solve as the Maxey-Rayleigh for a given particle. So the interesting thing is that in this entire Maxey-Rayleigh equation, there's only one non-dimensional variable which enters, which is the density ratio. Density ratio expressed in terms of R. Because of this magic length scale, all other parameters went away. So if you fix a density ratio and you solve this for one particle near one vortex, you've solved it for all particles near all vortices of that density ratio, so long as your particle Reynolds number is small. So you don't need to solve it for different vortices. So you just solve for one particular particle. Its Stokes number could be anything you like, but there is this additional thing, which is because it is a Lambosine vortex, there's one property of the vortex, namely its thickness, its width compared to this length scale, which appears in the flow part. It appears in the flow part of it. And so like even then you have only these two non-dimensional numbers because of the magic length scale. So, and if I had a point vortex, then this length scale doesn't exist. Or if I had a very heavy particle, then this gets absorbed into that and you'll still have just one non-dimensional number. So let's move on. Yeah, so first thing to note is that the Maxey-Rayleigh equation, which describes the unsteady Stokes flow for a little spherical particle, is not a dynamical system. It's an integral differential equation of the most horrendous kind, where you have an initial condition, the initial difference between particle and fluid velocity gives you a singularity at time equal to 0. And then there is this integral. So imagine, like, if I want to solve for one teeny particle in a cloud, and we know there are, quadrillions of them in a cloud. In order to solve it correctly, we actually need to remember its entire history from the time it was born, from 0 time. So you remember its entire history in this term. So like I have to remember its acceleration long ago and the fluid's acceleration where it was long ago. I have to store this in an infinite array, like ever increasing array, and perform this integral, which also goes through a weak singularity at the final time. So not only is this thing very singular, it's very computationally demanding. So in order to, and this term is called the Bassett-Boussinesq history. So this is a famous term called the Bassett-Boussinesq history, which is one of the forces acting on the particle. So the force acting on the particle depends on everywhere it's been all through its life. So that's the present force acting on it. And this can be derived quite nicely by, impulsive, a body starting impulsively. You can actually do this derivation, it's fun. So this is just to remind you, the capital R is a measure of the density ratio that we have. So this is the Maxey-Rayleigh equation. It is not a dynamical system. We have a very nice way of solving for this, and here's where I boast a bit about it. Haller actually wrote a focus on fluids article on our 2019 paper, and he said that the Bassett-Boussinesq term, this term, is notoriously difficult to handle, and so most studies ignore this term despite ample numerical and experimental evidence of its significance. So they're not dropping it because it's very small. Technically, it's, square root of Stokes smaller than this one, but the prefactor can be extremely large. So technically, you're keeping everything to order Stokes and not Stokes to the 3/2 or something. But there's no other reason, there's no real reason to drop it. But people drop it just because they cannot handle it. So like there have been several attempts, of course, to approximate the integral. And what we have is like an exact solution, no approximations. So what we've done is the following, and this is Vishal, my collaborator's idea. So here we have an ordinary differential equation in time. If you stare at this term, you'll recognize that it's actually a half derivative. It's a half derivative in time. There is this fractional calculus meeting going on here, right? So maybe I should be giving this talk there and not here. But yeah, this is actually a half derivative in time. And you see a real reason why you need to study fractional derivatives. So like Vishal's idea was very nice. He said like normally, he said that why don't we write this fictitious heat equation in a fictitious variable x. It's not the other x that we're talking about. This is a fictitious variable. And so a half derivative in time will become a full derivative in x. So if you do this, you can actually solve the heat equation pretty easily and you can get answers for this thing. So like this, I love this thing because like from undergraduate days or whenever it is, every time you see a partial differential equation, you're told first convert it to an ordinary differential equation if you can. And that's your way to simplify life. Well, here is a situation where we started with an ODE and to simplify life, we made it a partial differential equation. So that I really liked about this. So when you write it in this way, this entire term just becomes a QX. So like we've replaced this horrible thing by this, and this not only makes it look smaller and cuter, it actually saves on memory. So you do not have to remember the entire history. You can only remember a few Fourier modes, and that's what I'm coming to right now. And this becomes a nonlinear term in the particles frame of reference. It's nonlinear because you have Q, which is the difference in velocity between particle and fluid, and you have a grad U, so it looks as if it's linear in Q. But wait, this grad U is the fluid's velocity in the place where the particle is now sitting. So it's a function of the particle's location. And the particle's location is an integral in time of its velocity. So it's a very horrendously nonlinear equation. But the beauty is that in many nice situations, this way of looking at it lends itself to analytical solutions. So we have probably the first several analytical solutions of the complete Maxi-Rayleigh equations, including one for Couette flow. So like locally, if you can model your turbulence as a Couette flow, we have a way of analytically writing down the solution to the Maxi-Rayleigh in turbulence. So we do not have to solve, you know, this particle equation with the Bassett-Boussinesq term. So am I getting that point across? We can actually solve it in turbulence. So that's the basic message due to this analytical solution thing. But then what else can we do with it? Yeah. So now what we can do is we can, we've created this imaginary, fictitious variable X, remember? And this is my time in which I want to solve for everything. And it turns out that the Maxi-Rayleigh, the entire equation forms a Robin boundary condition. So when X is equal to 0, you get a condition which comes out of the Dirichlet-Neumann map of this thing. When you write the Dirichlet-Neumann map, you see that this Robin boundary condition imposed on this time boundary at X equal to 0 is exactly the Maxi-Rayleigh. So if you solve this, you've solved the whole thing. So what we do is we divide this time domain into boxes. And the moral is we solve it inside each box, the heat equation, and then we can store it on all these m delta t's. Once you store the solution at this place, and 10 Fourier modes are way more than enough, like typically 3 or 4 Fourier modes are enough in this fictitious space variable. Once you do that, you can forget about its entire history. So we've actually converted a thing which was not a dynamical system into some kind of a dynamical system in this history variable. We've made it all local. So the equations are horrible, but the message is that there is this history term which can be solved if you know the history term at one time step, one delta t ago. Like if you know the history term on this red line, you can directly solve for it on this red line. And then like if you, and that history term when you integrate and along with the forcing term, the nonlinear term that I talked about, we have to do some iterations for this if it's a very complicated nonlinearity. Then you solve for this Q, which is exactly the thing you want. It's the particle velocity minus the fluid velocity. So that is the solution to the Maxi-Rayleigh. So we solve it as, you know, integrals in this fictitious wave number space. And in many situations, you can actually reduce this to exact analytical expressions. So like the moral is we need far, far less memory. We're encoding the entire history in less than 10 Fourier modes in X, as opposed to endlessly growing storage, which you're going to need in time. And on top of that, we get spectral accuracy for any initial condition. So even in those situations where you cannot do it, you know, with the analytical approximations, you can actually solve this thing, which is not as horrible as it looks. It's a lot nicer than solving for that awful integral from 0 time to this time. Okay, so now let's look at what happens near a single vortex. So that's the problem we started with. In other words, we're going to solve for this thing with particles near a single vortex and ask what their dynamics is near the single vortex. And we know that this is crucial for understanding turbulence. So at large R, at large distances from the vortex, you can actually write down the solution by hand and you get this nice expression where you can see how it goes in time. You can solve it exactly and you get Fermat's spiral out of that as promised. So then, and that is the density ratio to remind you. This is now the du dt, the Lambosine vortex acceleration in space. And I mean, it's basically a u dot grad u term. Now, you can see from this expression, the r dot, which is just the radial velocity of the particle, that velocity is negative for a light particle when r is greater than 1 and a positive for a heavy particle. So this is just telling you a trivial thing that it's going to centrifuge out or in depending on whether it's heavy or light. But based on, but you can solve it exactly. And here we've done it for an r equal to 0 particle with and without Bassett. So without Bassett is the dashed line and with Bassett is the solid line. You see that at short times there's a difference, but at large times they asymptote to the same thing. But this difference can make a huge difference in many things, like in the void size, in the collisions and everything. So Bassett-Boussinesq history matters at early time for a vortex. And note that this flow is compressible in the particle velocity field because, you know, it's voiding from the vortices and collecting elsewhere. Okay, so here are the solutions. Are you able to see this red line? Yeah. Okay, so like this is without history and this is with history. So far away we see the Fermat spiral, but very inside the vortex, and this line, I mean, this color shows you the velocity in the vortex. You see that this particle spends a lot of time inside the vortex. It just goes back and forth inside the vortex. So it does, you know, this kind, here's the radial position and here's time. So you see that there is a large number of oscillations it performs inside the vortex before it starts centrifuging out. So the point is that this thing which we trivialize by saying that heavy particles are centrifuged out of a vortex is simply not true. They can spend a lot of time going back and forth inside a vortex. And whether or not you have history, it's the same thing, but with history, you have fewer oscillations. And you see that the long-term, you know, radial position is very different with and without Bassett. So the amount of ground it covers, the amount it's going to collide with other particles, perform collisions and coalesce with other particles to make raindrops, things like that are going to be very different with and without Bassett. So with Bassett, this is the spiral, and at long time, and without this. So you can get all of this from knowing, I mean, and since we are solving this for a set of vortex sizes, we can actually generalize the statistics of this to real turbulence. And so we need not even solve for real turbulence. So the finding is that the particle dynamics is very different from what you'd get from a, trivial minded field description, but all is not lost. You can actually use analytical, basically pen and paper solutions of the kind we wrote down to, generalize with statistical approaches. And in turbulence, we know there's vortices, but there's a range of circulations and intermittency. All that can be taken into account by just changing the circulation and things in our thing. And even for a range of particles, big particles and small particles can, cross each other and coalesce. You can calculate all of those things. So thanks for your attention. That's what I wanted to say today.
Any questions? Oh, let me start from over here.
So you said that there are discrepancies due to Basset-Boussinesq's force, but this, I guess, will depend on the density ratio. So for which values is it becoming significant?
Yeah, so we've done this for a range of density ratios. And you're right that, it depends on the time for which you're running it, and it depends on the density ratio. Here we put a typical density ratio, which is, R is 0.67. So it's like the density ratio is 1.75. So like suppose you have plankton. Yeah, it's not almost neutrally buoyant, it's like twice the, so like plankton and, many sedimenting things in the ocean, they have this kind of density ratio. We've also done it for cloud, namely when R is practically 0. And we don't see oscillations, but we see big differences here. So like somewhere or other, it matters whatever be the particles. So the two things we were interested in were, things sinking in water and clouds. So for both of these, the Basset term is very important. Does that answer your question?
I'm curious, did you use the unified transfer method because Vishal was in the room, or is it crucial to the solution?
Both.
Okay.
Yeah, Vishal actually walked in when Ganga and I were discussing this.
So you think the solution to this PD requires that transform method, or?
Yeah, it makes it possible to get these analytical solutions, which I simply don't know how else you would ever get.
Okay.
So like we could actually write the global relation, and that reduced one of the unknowns. So the algebra was very messy, but basically possible because of the unified transform method.
Good, thank you.
Excellent talk. I used to do Rayleigh Taylor instabilities.
Okay.
And I downloaded your JFM article to certain of your equations. So you're at time advecting the vorticity and the density, and then you must have some incompressibility part of your code where you get out the velocities.
Yes.
Now, this is something I'm only fully becoming aware of now. I've known for 10 years for my type of problems that there's an issue with using the Lamocene vortex profile, which my community usually calls just a Gaussian.
Right.
And there was this horrible controversy, a lot of it took place in this room, about whether Euler had a singularity or not from a particular type of initial condition. And at the end of that, these exchanges between 2008 and 2010, I came to the realization that we were all using some version of the Lamocene vortex profile, and that we were getting different results because something was unstable. And I concluded that I need to use a different profile, which I now know a certain branch of the mathematics community has been using for their own reasons, and they call it Kaufman-Scully.
Okay.
And I call it the Rosenhad regularization of a point vortex because that's where I hear about it from Biosavar and from my MHD colleagues. And what I discovered at the previous workshop, one of the presentations, I saw they were using essentially the same profile I now use, but they were mathematicians who presumably had real justification for doing this.
Okay.
And so there is. And so we need to discuss this outside of this room, but within this institute. So it's a comment I wanted to make.
Okay, so one thing I should mention here is that though we've used a Lambosine, we've done calculations with Rankine vortices, and we've used other kinds of profiles where, you know, strange profiles, and our results are more general. I mean, nothing we're saying, of course, quantitatively it's going to be different, but we can do this with any profile you like. And in a three-dimensional flow, we might well have to.
So thanks for the very interesting talk. Just a quick question on, maybe you addressed this at the very end. So presumably this is in some dilute limit. I mean, what happens if the particles were to interact?
Yeah, so that's an important question. Like whenever you have, so at this point, we don't have a very good method to do unsteady Stokes with interacting particles. We can only pretend they're Stokeslets and that they don't see each other's unsteadiness, which is slightly wrong, but that's the best way we can handle interacting particles right now. But we need better methods than this to actually handle that.
Any further questions? There are no questions from the remote community, so let's take the speaker again.
Thank you.
And we have a, well, 7-minute break before the next talk.